How does critical magnetic field affect room temperature superconductors? Imagine a world where electricity flows forever without losing energy, right at everyday temperatures. That's the promise of room temperature superconductors. But there's a tricky part: magnetic fields. They can make or break these materials. Superconductors are special because they carry electricity without resistance, but only under certain conditions. One of those is the critical magnetic field. This is the maximum magnetic strength a superconductor can handle before it stops being a superconductor. If the magnetic field gets stronger than this limit, the superconductor loses its zero resistance property and acts like a normal metal again. This can happen even if the temperature stays below the superconductor's critical temperature. For room temperature superconductors, this is especially important. Most superconductors known today only work at extremely cold temperatures. Researchers are trying to find materials that can superconduct at room temperature and normal pressure. Even if they succeed, these materials need to withstand strong magnetic fields to be useful in real life. Think about magnetic levitation trains or powerful MRI machines. They generate huge magnetic fields. If a superconductor can't handle those fields, it won't be practical. There are two main types of superconductors. Type 1 superconductors are simple metals with a single critical magnetic field. Once that limit is crossed, they stop superconducting completely. Type 2 superconductors are more complex. They can handle much stronger magnetic fields because they enter a mixed state. In this state, some parts of the material stay superconducting while others become normal. This allows them to work in higher magnetic fields before losing their superconducting abilities. For a room temperature superconductor to be truly useful, it needs both a high critical temperature and a high critical magnetic field. If it can't resist strong magnetic fields, it won't be able to operate in environments with powerful magnets. This makes the critical magnetic field just as important as the temperature. In short, the critical magnetic field sets a hard limit on how strong a magnet can be before a superconductor stops working. For future room temperature superconductors, having a high critical magnetic field is key. It's what will allow these materials to be used in everyday technology and revolutionize how we transmit power, run electronics, and even move objects with magnetic levitation.